So welcome everyone to the third event of the Connecticut River Joint Commission's Riverwide Speaker Series. Tonight, our topic is engineering with nature. And I'm really excited for us to talk about retrofit stormwater management that can minimize the impacts of existing development at sites that either lack stormwater controls or have insufficient controls in place. We're going to hear a lot about a manual for stormwater retrofit that was put together in part by our speaker, Theresa McGovern. Theresa is a water resources engineer with VHB. She has extensive environmental consulting experience with focus on watershed evaluation and planning, water quality modeling, TMDL compliance, hydrology and hydraulics, and stormwater management and design. She enjoys using technical approaches to develop creative and pragmatic regulatory compliance solutions. So with that, I'm going to step aside and let Theresa take it away with her presentation. And afterwards, or even during, people can feel free to pop your questions into the chat, and we'll also have time for question and answer afterwards.
Well, it's fun to see some kids in the background. You might see mine at some point as well. So thank you for joining live, and hopefully we do get some people watching the recording also. Since it is a small group, definitely feel free to ask questions on the spot. And you know, Olivia, if you want to just interrupt me, because I get distracted if I have a presentation up, but it's easier to kind of ask things in the moment and get feedback. So definitely take advantage of the small group and ask questions along the way. So yeah, why don't I share my screen, which I'll start my presentation, and I'll have to make sure everything works and put you guys over there. Okay. Can you guys see everything the way you're supposed to?
Working great.
Okay. So yes, my coworker Nate is not here tonight. It's just me. But we kind of have been on this roadshow trying to promote this new manual that VHB and myself co-wrote with the UNH Stormwater Center, Jamie Houle, and we had a really collaborative relationship with EPA also as we wrote this. The funding actually came from the SNEP program, which is the Southeast New England program. They get a lot of funding through EPA, and this idea sort of sparked from EPA, and this was a way for them to get it done. And it's really, focused on guidance for the whole New England area. So, yeah, so what I'm going to do today is give just a little bit of background of what this manual is, why it even came about, how it kind of fits into the bigger picture. I do have this, I was saying to Olivia, it's this presentation is one we've given to a bunch of different groups, and I was just, getting to know your group a little bit more. There is some maybe more technical stuff in here that maybe I'll spend a little less time on and more give the background and the context of what this is, what it has in it, how it could be used as a tool. So if I'm spending more or less time on different parts, just let me know and I can, tweak it. But I was trying to get the best understanding of what you guys might care about. So, talking about some of the highlights of what's in the manual, obviously we want to encourage people to go check out the manual. Olivia, are you able? I know you get your hands full, but maybe at some point during this presentation, if you can throw the link in the chat to where you can download the manual. And we also have a 2-page summary sheet that we like to hand out when we're giving talks. And it's also a nice thing to share with someone else if you want to say, hey, check out this manual, it might be useful for what we're doing. And instead of having someone to have to flip through it, we have this 2-page sheet. The first page gives a nice summary. So if you have your hands full and can't get it in, I'll get it in at the end. So all the stuff's available. And then I'll talk a little bit about how the manual could be used, and maybe I'll try to spend a little bit more time on that part with you guys. So yeah, I can see the video, but I can't see the chat unless I do something different. So I'm gonna just know that I can't see the chat. Okay.
I got you,
So,
Teresa, and I
all
just put
right,
the
thank
link
you.
in.
I know. Oh, awesome. You're very good at multitasking. Okay, so I like to start with just some definitions because everyone uses these stormwater words their own way and differently. So the first definition is retrofit. This is the New England Stormwater Retrofit Manual. And so what do we mean by retrofit? And everyone has different ideas about that. For this manual, we left it pretty broad and basically said any stormwater retrofit is the addition of stormwater controls on a currently developed site. So that's, a building with a parking lot that is now going to go do some work there and wants to add stormwater control. It could also mean you have a detention basin and you want to change that into something that, does a little bit more for water quality. So it's a pretty open-ended definition, and we tried to leave it that way so that because these techniques and these approaches really apply to any sort of constrained situation, basically, where you're trying to do the right thing and add water quality. Yeah, and then we use the term stormwater control measure to mean something like a rain garden, a bioretention system, an infiltration basin. So anything that BMP is another buzzword that everyone usually uses, and I will probably interchange the two during this presentation. But what we're generally talking about are something you're building, installing to enhance the water quality treatment of the discharges from your site. So yeah, so just some of that. So when we started this manual and like why this was even something that came about, EPA and the different SNEP group and stormwater, the UNH Stormwater Center, and like everyone kind of who's in this industry was realizing that we have these very prescriptive pieces of guidance from the regulatory world that has been built on kind of the same old research that's a little bit dated, and it's very conservative. And so we wanted to pull together the research-based guidance that's out there now to help support the planning, siting, and designing of retrofit BMPs. We wanted to give a framework of how you might select optimal BMPs for a specific project or site and present this way of crediting those measures. So a lot of times we have these good ideas and we know it's the right thing to do, but we need that way of actually showing credit or value to those so that we can justify it or show that it's cost effective or sort of worth it. So we wanted to pull this together in some guidance, and although there are a lot of manuals out there, there aren't any that are really for this retrofit scenario where you're really constrained, but you still want to do the right thing and add something to the site. And this big asterisk at the bottom is that this is for scenarios where the regulatory requirements do not dictate a prescribed approach. So we're not trying to replace any like state standards or other regulatory programs that are dictating what you need to do. Obviously, if those are there, you have to do that. You have to do what they're telling you to do, and we're not trying to like, supersede that. This is to really fit a space where you have more flexibility in a regulatory side, but you are trying to kind of go back and do the right thing. And so when we're talking about this, we're thinking that, there's scenarios where you might have a TMDL, a total maximum daily load. There's sort of a water quality requirement because the water body is impaired. And, there's this drive to go and improve the discharges. So that's a space where, you're not necessarily trying to do this to meet a newer redevelopment standard. There's also, just sort of watershed initiatives. If you have like, a really key lake or pond that's serving, the economy, your recreation, all those things, there's a drive to improve water quality for those reasons. And we're also starting to see these other regulatory programs that are requiring retrofits, including the residual designation authority permits that are coming through EPA. And I know Vermont has those, and now Massachusetts has draft ones for 3 watersheds. And so this is a new permit that permits these private properties that have a large amount of impervious cover, and they're being required to go back and add stormwater control measures to improve the conditions. So there's a lot of like niche areas where stormwater controls are needed or desired, yet we don't necessarily need to follow the very hard and sometimes restrictive prescriptive guidance of the state manuals for new and redevelopment. And so what we were seeing is that when we wanted to do something just to improve the water quality for the greater watershed benefit, designers were going and defaulting to the kind of strict guidance from these state manuals and saying, well, I can't fit that. It doesn't work. You know, I can't make it big enough. I can't add all the stuff that they're asking for. I can't design it to those specifications. And then they would do nothing. And, you know, logic says, you know, something is better than nothing. And so this guidance is meant to kind of show, you know, designers in particular who are, you know, kind of trained on this way of approaching a site and approaching stormwater to, you know, break out of that and think more creatively and find an approach that will work to actually get to solutions. So I think I covered a bunch of this in my little monologue there, but so this manual, you know, we're trying, like I just said, we're trying to encourage designers to move beyond these prescriptive, you know, set of standards that they're kind of trained against through doing these site projects. We're helping designers piece together and kind of think creatively with their designs to get to the best control measure that would fit these more challenged and constrained sites. And we want to promote the use of these EPA curves that I'm going to talk to you about in a little bit more detail. This is a new tool, an accrediting approach that EPA developed. They've been out there for a while, but they're still not being used you know, widely, but you'll see these curves and this tool in the New Hampshire MS4 permit, the Massachusetts MS4 permit, Vermont's using it for all the Lake Champlain accounting. Rhode Island is starting to adopt it in some of their compliance requirements. So this is sort of like the new way of accounting for stormwater. And so, you know, we wanted to put that approach into a manual that wasn't a regulatory permit. You know, people aren't like digging through regulatory permits and like, ooh, let me see what's in there, you know, like, so this is a way to have that guidance in an actual guidance document. So, and I'll introduce what those are and explain it more right now. So I'm guessing just with the small group and the varied background that you guys maybe aren't familiar with these curves. So I'm going to step through and introduce them to you and explain why this is such an important tool as we're talking about stormwater improvements and retrofits in particular. So EPA a while back developed these curves. We're calling them the performance curves, or, you know, SEM performance curves. They are a set of curves that give you information about how well a BMP or SEM does at removing certain pollutants. So I don't know if you can see my pointer, but the x-axis is considered the runoff depth from impervious area. So that's a mouthful, but it's basically, if you think about it, it's like essentially the volume of your BMP, of your SEM, divided by its contributing area. So it kind of just normalizes it so that it's, you can say this BMP treats an inch of my watershed. And, you know, that way, if it's a small one that treats a small catchment or a big one that treats a big catchment, you can say it's kind of, it's, you know, sized for that, you know, ratio. And so think of the x-axis as basically the size of your BMP. And the y-axis is your percent removal of a given constituent or pollutant. And so, and then EPA developed a unique set of these curves for a whole slew of BMPs. So I'm just showing the one for gravel wetland right now, but they have I don't know, like about 10 of these curves, biofiltration systems, infiltration systems, and a whole slew of others. And then there's an individual curve depending on the pollutant that you're interested in, or that BMP has been measured to perform against. So these curves were developed by EPA by taking actual data from the UNH Stormwater Center. That center up at UNH has a bunch of BMPs that are in place, and they measure the influent and effluent and measure actual pollutant removals for a slew of storm events. And so EPA took that data and then developed models of these BMPs to simulate what's actually happening, and then we use those models to kind of extrapolate and create these curves. And so they took the model and ran over 20 years of actual rainfall data to figure out how these BMPs would act, with lots of varied precipitation conditions, like actual data. So you'd get, back-to-back storms, small storms, big storms, anything you would normally see or had seen had been measured for those, I think it was like 24 years or so. And so what they did was they ran it all and then took the annual average performance. So on an annual average basis, if a gravel wetland was one, size to be, 1 inch over, over that contributing area, how would it do at removing total suspended solids or metals or whatever it might be? And so these curves can tell us, and logically thinking, as your BMP is bigger, it can capture more storm events, it can treat more, more water. So as it gets bigger, your performance goes up. And so these curves can be used, two different ways. The first way is saying, on my site, I want to get 60% reduction. How big would this BMP or SEM, I'm sorry, I'm going to use those interchangeably. How big would it have to be if I wanted 60% reduction? And so you start on the y-axis and you go back down and say, okay, it needs to be this big. Alternatively, you can say, I have a BMP, or I have the space to make it, 1.2 inches. What kind of treatment would I get for that? And so you can go the other direction. And so these are really interesting tools. And just to kind of put that in context, a lot of the state standards and kind of the way stormwater had been typically being done previously in sort of the regulatory world is they would say, build your BMP to 1/2 inch or 1 inch size. And if you do that, then you can check the box that it gets 80% TSS removal or whatever this goal is. And so you had to build it that size to check the box that you've met the water quality standard. But like I said, in these retrofit constrained scenarios, you can't always build it that size. You might have only this much space or whatever. And like I said, it was kind of, we've gotten into such a habit or such a thing where we're just looking at those standards and trying to check those boxes that designers and would say, well, I can't build it to 1 inch, so like forget it. We have to do something off site, or we can't say that we met it, or whatever the consequence was. But they would sort of skip it all together. But logically speaking, building something, even if it's half the size, is going to contribute. So these curves basically now put numbers to that and say, yes, it does still provide value. Here's the value it provides, and actually gives you that information. So another way, as you start looking at these curves further, you can see that they're giving you information about, starting to think about optimizing and being cost effective. So as I said, the curve is a curve, it's not a line. So it's not like saying, if I do 1/2 inch, I get 50, and if I do 1 inch, I get 100, that would be a straight line. It's really that, it's a curve. So the knee on the curve is basically where it goes from, each little incremental increase in size gives you a big addition of treatment. And then as you keep getting bigger and bigger, that return on size gets smaller. So there comes a point where you can make it bigger, but it's not going to do that much more for water quality treatment. And so we're calling that like the knee of the curve. And that's sort of that optimal point. your kind of like return on investment starts diminishing. And so this is really valuable information when you're trying to think about retrofits, not just for a site, but when you're actually trying to plan maybe retrofits for a watershed. You can say, I'm not going to go building, 1.5-inch basins everywhere when I could make them, 0.6 of an inch and get almost the same performance. I can build, 3 of these for the same cost as one of those bigger ones and get, more water quality treatment. So as you're starting to like think about, bigger scale planning, this is really, really important and useful. And it's also really useful, like I said, on that site scale when it encourages people to, if they can't meet the kind of, standard rule of thumb, 1 inch or 0.5 inch, it says, hey, this is still valuable to do it, even though it's smaller. So this is really kind of important tool. And like I said, these curves are showing up in the New Hampshire and Mass MS4 permits and the Vermont Lake Champlain. It's their way of tracking and accounting of BMPs to meet impaired waters and TMDL targets. Just making sure I say everything. So this concept of the knee on the curve is something you could use. So what we did is you just took a sample curve. It's for an infiltration basin, and EPA has curves for the infiltration systems. They actually vary it based on your soil type because sandy soils are going to infiltrate more and, tighter soils are not. So they actually have different curves for different infiltration ones. So we took the curves for hydrologic soil group C and, of course, my dog opened the door, and plotted the knee on the curve for each of the different curves. There's a curve for each pollutant. And so you can see that, and infiltration is a great example where the curves can be very, very steep because you're infiltrating a lot of these small storms where a lot of the load comes from. You can get a lot of the pollutants out, even with a small system. And some of the more kind of trickier pollutants or just the volume itself as runoff, might take a little bit bigger of a system. But this kind of gives you another way of kind of using this optimization concept with the curves. And I do want to point out that, the reason why the curves are, a curve and not a straight line is because that understanding that, this first flush concept where you have this buildup of pollutants on these impervious surfaces, and then it rains, and most of that load is coming off in those that first flush. And so the smaller repetitive storm events are adding most of the load on an annual average basis, or that first flush. So even a smaller system can do a whole lot because it's that those smaller systems are capturing all those small events and all that load. So it's a little bit different thinking than when we're talking about resiliency and flood protection and all that. That's when we're talking about, the big events, right? And needing the volume and the detention and the timing. This is more about, water quality is more about the load and that sort of repetitive addition of each of those small storm events. So for these types of measures, you can get really small. Are there any questions before I kind of move into another section? Any questions about the curves or, oops, how do I go backwards?
Theresa, are there curves for runoff coming from other types of areas like an agricultural field or just non-point source pollution? Does this apply to
Yeah,
those?
that's a great question. And I don't really usually get into this, but I'm glad you asked. So the curves are the percent reductions based on a given pollutant. So it's like saying an infiltration basin would get 50% reduction of phosphorus, regardless of where it's coming from. It's just, if it's coming in, it would remove 50%. And when you want to start talking about the actual loads, like, well, how many pounds of phosphorus is that? That's when you need to apply a loading rate that is associated with that particular land use. So maybe agriculture produces, X pounds per acre on average of phosphorus, and residential produces that much. either, so the curves aren't super specialized to like which land use it's coming from. It's the percent reduction. And then when you want to get into the actual pounds or loads, you can apply a loading rate and then you can apply the percent reduction to that mass. And so EPA also has loading rates based on the different land uses. They're simplified, they're not super site specific, it's just a set of values. There's a lot of other loading rates that are out there that you could use that, would apply, but we did include those loading rates as an appendix in the manual and have a little section talking about how to do this accounting as a mass, not just as a percent reduction, as like actual pounds. So that is in the manual if you want to kind of like understand that concept.
Thank you. I see Barbara, you have your hand up.
Yes, I do. I'm on a conservation commission that sometimes reviews site plans, and if there's people will come and they'll say, the developer will say, well, don't worry about the runoff because all of the water that's coming off the roof and through the parking lot with the salt and the oil and all of that goes into a catch basin and it will magically come out into your wetland just fine. Is this what we're talking about? These kinds of catch basins where runoff is collected off a parking lot into this magic area?
Well, you know what? I'll talk a little bit about that in a minute, but a catch basin, so what I would call a catch basin is like, it's an inlet. It's like part of your conveyance system. Yes, some have deep sumps that let the solids settle out and do a little bit of pre-treatment. But what we're talking about here are actual designed stormwater treatment measures. Like, you might see them often as like a detention basin, like at, the Home Depot parking lot. They're always there, those big detention basins, because they make them huge for like the peak rate control and the volume control. But we're talking about kind of the treatment measures like infiltration basins, bioretention, rain gardens, gravel wetlands. These are specific systems that are designed for water quality. A catch basin is not one of those, but they do have these proprietary systems that are out there. Like you'll see storm scepters or vortechnics, or basically there's these, bigger box systems that are often underground that have been, engineered to vortex the water to get more of the solids out and blah, blah, blah. And, so there's a lot of those out there. And I know developers like those a lot because they're underground, they're out of sight. And the manufacturers tell them that they can get all this, pollutant reduction for them. But those have really varied results, and you're usually focused on getting the gross solids, the heavy stuff out, which is great. But a lot of if you're, worried about, bacteria or, the nutrients like nitrogen and phosphorus, a lot of those are on the smaller particles or dissolved, and those aren't getting out through those settling type systems or, the vortex systems. So you might be seeing, those might be the magic boxes that they're promoting, is these we call them like just proprietary systems, hydrodynamic separators, because there's so many companies out there like creating these products, trying to find the silver bullet, to magically make this all work. So these are more like engineered designed systems that usually flow through, but they can also just take the first flush and let the rest of it go downstream. So
thank you.
All right. I'm going to keep going unless someone wants to chime in. So we talk about in the manual this how to choose and select and design your SCM, your BMP, your engineered treatment system. And again, we're kind of fighting against what's gotten people used to into the design world of just picking one off a shelf and saying, I want a gravel wetland, here's the spec and design criteria, and I'm just going to plop it in on my site, and kind of skipping the part about, thinking about what they need on their site, how it works, and engineering it to adapt to your site. Again, very critical for retrofit when you're constrained. You need to be creative. So we kind of brought it back to the basics, which is talking about the unit operations and processes that actually treat the pollutants or bacteria, you know, or whatever your metals or whatever you're interested in. And these really come from wastewater, but it's the same thing. So, you know, you have the hydrologic, physical, chemical, and biological processes. So like a hydraulic, hydrologic one would be like infiltration. Physical is like filtration, actually pulling it out. Chemical is like nitrogen, nitrification, denitrification. So actually like a chemical process that's happening. And biological would be something like adsorption from plants. So all of these things are happening in the varied BMPs, you know, so an infiltration basin, the primary one is, you know, that infiltration, actually infiltrating the water, removing the water, not having it be a surface discharge at all. It's going into the groundwater, but also filtering is happening through the soil, and there's sort of you know, plant interaction going on. So there's usually a lot of these are happening in any one of these systems, but when you start thinking about how they work in the primary ones, you can start to actually get more empowered to design your system yourself instead of just picking something off a shelf like a black box. So we set up these crosswalks, and this is just like a snippet of it because there's a lot of these different BMPs. But basically, what we are connecting is these unit operations and processes to those curves I was showing, and what people call them as different BMPs or SCMs. So what we see a lot in this middle column is, you know, this list of BMPs. Oh, you can pick one of these in a state manual, or here's the set specs for these different names. And some people call them, you know, a rain garden. Some people call it a bioretention. You know, then you get into all the nomenclature. Are we talking about even the same thing? And it kind of people get lost in that space. And what we really want to do is say, well, what's actually happening in that system? Oh, it's infiltrating, it's filtering, it's whatever. And so whatever the primary operation is, you can then link that to the EPA curve that was developed based on that type of process. So if I can use the infiltration basin curve when I have any system that's infiltrating like a basin. So it could be a swale, it could be like a leaching basin, it could even be a rain garden that just doesn't have an under drain. You know, we're saying with an under drain, then it becomes a filtering system because then it's discharging. But if you have just any sort of depression that doesn't have an outlet, that's essentially acting like an infiltration basin. So you can link it to that curve no matter what you call it. And that's very, again, empowering because now I can be creative on my site, design something that maybe doesn't match someone's definition of whatever the BMP is, but I can show them still that it's, you know, doing something to benefit in performing and having that water quality. So this is a way to connect these concepts together and, again, empower designers to think about what's actually happening and what kind of system they need or want, and then be able to credit it and, you know, value it and account for that. So kind of to get to your point, Barbara, like a whole system would include many different components. So we talk about, you know, more briefly, but we talk about these functional components, which are collection and distribution, things like curbs, catch basins, you know, the piping and all that to get the water, you know, where it needs to go. Even your grading is kind of part of that, right? Like your topography and how you slope the sites or whatever. We also put pretreatment in that bucket because that's part of how your system works. So pretreatment could be like that deep sump in your catch basin. It could be a trash rack. It could be a sediment forebay. It's the things that are kind of getting the big stuff out and separating that out into a concentrated area so that you can more easily maintain the rest of the system. So that's part of how it functions. And then you have your treatment component, which, you know, we're showing a basin here, but it could be lots of different things. And in the manual, we talk about these different categories and discuss them in more detail and give some guidance about how you'd select them and design them. But what we want to show is that these treatment components are really, and we've grouped them based on these unit operations and processes, actually how they work. What are they actually doing to do the treatment? And again, that links to the curves themselves. And then you still have, at the downstream end of your system, you have to think about discharge and how is it getting out safely, and how am I making sure it's just the right amount of water staying in there the right amount of time. So these are all the different pieces you would need to design a BMP, and especially like I was saying with the retrofit scenario, these constrained areas, you have to be creative on all these pieces. You have to think, how am I going to get the water there? This is already built this way. This is already graded that way. Or, I only have so much space to do X, Y, and Z. And so we talk about this as sort of the Mr. Potato Head version of it. It's like, I need to have all these different pieces I can pick from and put them together into something that fits for my site. And so we go into this in more detail in the manual. Are there any questions now? And then I'm going to get into some examples of some of the guidance, and this might get a little more technical, but I'll go through it, and then people have questions they can ask. And my dog's such a pain, so let me know if there's any questions now.
Keith Alverson did put one question in the chat a little bit earlier, but you probably can talk about it now. He asked, some pollutants magnify through the food chain, mercury, for example, and do you look at these?
No, I mean, not like that. I mean, mercury is like that thing that's, like you said, in the greater food chain, it's probably magnifying. If we're thinking about typical stormwater pollutants that you might see on impervious areas, things that are coming off of cars or run on, from soil that is nearby, like eroding soil or atmospheric deposition and stuff. Those are the types of pollutants we're looking at and treating them sort of like at the source, pretty close to the source. We're not treating it on the pavement, but we're collecting it and treating it right then and there. So not thinking of those greater food chains, but one point that's sort of similar to that idea is that there's certain types of vegetated systems that have been shown to actually increase some of the discharge of this. So if your issue is, let's say you have an inland pond that has issues with algae growing and algae blooms, you might be really interested in phosphorus because that's the limiting nutrient for algae, and that's as much phosphorus as you have, as much algae you're going to have. And so you're trying to reduce phosphorus. You might have a system that is so well vegetated with these, like, maybe it's a created wetland and it has these great wetland plants and all this great stuff, but there's certain times of the year where maybe those plants are dying off or decomposing, and that discharge actually has a higher load of phosphorus than the runoff coming in from the parking lot. So there are some concerns like that, and there is some of that in the research that we see. And so it used to be like created wetlands was something that they, was like a go-to, and now it's like if your issue is nutrients, you have to be more careful with that, especially or if it's like bacteria and you have lots of animals and like the source you're trying to protect is right downstream of that. There are these cases where you kind of have to understand the whole system, but in general, the ones that we're talking about are generally, supporting the pollutant reduction of the stormwater. Okay, so I'm going to just step through some some highlights of the manual where we basically, coming from the design world myself and trying to work through these different standards and supporting site designs, and also these sort of bigger picture goals of trying to get, hit watershed goals, there quickly became like a disconnect there where, if we were trying to use these really constrained standards, we just weren't able to do everything that we knew logically was going to be an improvement or make sense. So this manual pulls together some of those major concepts and says, well, in the retrofit scenario, where you can be more flexible, you don't have to check all the boxes from the state or whoever the regulatory agency is. These are some things you can relax or do a little differently so that you still do something instead of skipping it all together. And this is all backed by research, and this is why UNH Stormwater Center is such a great partner, because this is what they do. They research all this stuff. So they know the latest science, and they know, that this is okay to say this for a design requirement. And what the manual does too is says, this is what's still really important. You need to follow these things, but here's some things that, maybe we can be a little bit more relaxed on. So I'm going to step through a few of those. One of them is this idea of separation to groundwater or bedrock. So when we're talking about one of these basins, especially the infiltration basins, a lot of the standard guidance out there or requirements out there is to have a certain amount of separation from the bottom of your basin to where groundwater is, like in a vertical profile. And that was based on, protecting the groundwater, making sure there was enough treatment happening from your stormwater before it got into the groundwater source. And that guidance was mostly based on septic system guidance, not really stormwater. And we know stormwater is a lot cleaner than septic system concentrated water. So in addition, a lot of the research is showing that infiltration in a grand scheme as a watershed management perspective, you want to infiltrate wherever you can. You want to recharge that water back to the groundwater aquifer. That is mimicking the natural hydrology the most. I mean, if you think about, you have these pervious areas, grass, forest, that water that falls there is, primarily staying there or staying really close to there. You add these impervious surfaces, and now you're getting that water out as quick as possible. And so, infiltration is such a critical tool, not just from water quality, but also from like a bigger picture watershed management perspective. And the requirements that are in a lot of the standards out there now are saying you need to have the separation or you can't do it. And so what we're saying is, okay, that's kind of strict. And when you're really constrained and you really want to do the right thing, like, yes, you do need some separation. Otherwise, you're not going to have infiltration. Your basin's going to be wet. But it doesn't have to be this 1 to 3 feet of separation. We're saying, try to do 1 foot of separation and have that 1 foot be a filtering layer, making sure it is doing that filtering so that it's essentially treated by the time it goes in. Another one we're promoting here in the manual is a measure that has been considered sort of low impact development type technique, but also is showing up in some of the manuals too. It's this concept of impervious cover disconnection. And so this image is showing so basically when you have an impervious surface and there's allowed, the runoff is allowed to sheet flow in a non-concentrated way off to these pervious areas. So you don't have a curb, you don't have a collection system. Country drainage is like another way of thinking about it, that runoff just flows into a grassy area, a forest, or whatever it is, and doesn't concentrate. And that is, talked about as a low impact development measure. It's also in some of the manuals talked about as a filter strip or this qualifying pervious area where it's given credit that way. And what's really cool is that EPA actually developed some performance curves to quantify how beneficial it is to do your drainage this way. And basically, instead of taking it as like a site design approach, we're actually kind of formalizing it as a stormwater control measure, as a BMP, and saying, this is actually a BMP. Like this, this grassy area, we could consider a BMP because it's receiving all this runoff from the roadway and treating it. And so by doing that, then you've now valued this area, and it becomes something that the owner needs to maintain like a BMP. They need to value it. They're less likely to obviously develop it because it's acting like a BMP. And and like I said, EPA developed some curves for this to actually quantify the benefit of this. Like we all know it makes sense. You're matching natural hydrology more. But how do you put a number to that so that you can value it and also say, hey, I'm doing the right thing just by this type of drainage pattern. And so these are the curves for that. It's a little different. On the x-axis, you actually have the ratio of the impervious area to the receiving pervious area. So, like roadway to grassy strip ratio. And so they have curves for pretty urban type areas on this left-hand side, all the way to that more kind of rural, or what we're using this upper end for is more of like that's highway situations where you have highway, and then it just goes into like a forested area, has a really large median. And what's nice about this is it really encourages keeping the runoff dispersed, not necessarily collecting it in a collection system just to stick it in a basin for treatment. It makes more sense to leave it as sheet flow, over a large area, just flowing into these pervious areas. And then it kind of forces, some of the entities who are using this as a formal BMP to track it and credit it that way. If they want to, then they have to maintain it and sort of put it into their system, just like they would an infiltration basin or a rain garden or something.
Theresa, we have one question in
Yeah.
chat on this specific technique and how it works with salt.
Salt is like the next frontier. I don't know what to call it. Salt is the tricky one because it's dissolved, and it will stay in your water column in the groundwater, and there is nothing that really breaks it down the same way, or filters it or treats it the same way we've seen with some of the nutrients and metals and even bacteria. So salt's a trickier one in general. This measure probably helps to some extent with salt issues, just because you're not concentrating the runoff in one place and making a super concentrated salty discharge, from your basin. It's sort of spreading it out. And you've seen, we've all driven on highways where you see that first 5 or 10 feet is kind of toasted grass, just vegetation that can't handle it. But so, if you were to use this measure in like a heavily salted area, you would want to have, some sort of sacrificial first set of length, and then sort of count the rest of it as, doing more of the treatment. Because the way this measure works, you need to have sheet flow, like non-concentrated flow. And it needs to be dispersed. So you can't have like really steep slopes because then the water concentrates. You need to have it vegetated so you're not just creating an erosion problem. So yeah, salt in general as a stormwater pollutant is just tricky. And I think that's kind of the next area for real research and understanding what to do there. What's like the good thing was that the use of sand went way down, and sand used to be a huge stormwater problem. There's like legacy like sand accumulation in like ponds and wherever you see these outfalls, and that sand just grabs onto whatever phosphorus and other pollutants just stick to that sand and get carried with it. So they drastically reduced sanding over the last 20 whatever years, but to then use salt. So now we're having the salt issues. So really, when we talk about BMPs for salt, it tends to be more how to reduce how much salt we use, not how do you treat it after you've dumped it all in the road. And that's kind of where that's at right now, which hopefully we'll have more research and we'll find some special organism that's like, chemically maybe treats it or something. But another thing that sort of bucks some conventional guidance is what we're saying about pretreatment. And so if I alluded to this before, we kind of in this manual lump pretreatment measures like sediment forebays and deep sump catch basins, and even those proprietary systems are often used as pretreatment. We kind of think of those as functional components and something to make your system work better, because that's what they're designed to do, is to have its concentrated place where all that stuff gets accumulated. It's easier to inspect it, it's easier to maintain it, it's because it's all there, and then you don't have to kind of ruin your vegetation or whatever else is going on in your treatment system. But a lot of the standard guidance requires it in a very stringent way and specific way. And again, on a constrained site, you might not have room to fit a sediment forebay that's sized X, Y, and Z. Or maybe you're trying to do a more dispersed system, so you don't have catch basins, and therefore you can't have a deep sump catch basin because you're trying to leave runoff more dispersed. So what we're saying in this manual is that pretreatment is more of an optional thing, but obviously heavily encouraged for the function of your system. This diagram here is showing just a creative way of actually doing pretreatment when you might not have the space. So this is a profile of a leaching basin, which is basically like a catch basin, a tank with holes in it to allow the water to drain. And usually what you'd want to do is get rid of the big heavy solids or any trash or anything so you don't clog that system up. And usually you do that as an upstream something, deep sump catch basin or some settling tank. Well, if you don't have the space for that, here's a way where you can just combine the two together. So you have the solid sump section on the bottom where all your heavy stuff can settle out. And then, you leave this upper space for where the holes are, where the infiltration can happen, and that leaves that cleaner. So, once you start kind of thinking about things a little differently, you can be creative and come up with solutions. But in general, we talk about pretreatment as, as a part of your function of your system. Another thing we've included in the manual and encourage is, like I was saying before, about how important infiltration is. EPA is really on with this idea and seeing that from a greater watershed perspective, like I was saying, Matt, getting water back into the ground is really important. And so a lot of state manuals will say you can't do infiltration if your soil has this infiltration rate or lower, or this hydrologic soil group D, which is usually a more tighter type soil. They won't even allow it. They just say, don't even do it, because you're saying, it's likely to fail, it's not going to work, or whatever the reasoning is. And again, what this latest research is showing is that you do get a lot of infiltration in these soils and in these systems. And oftentimes, like, previous thinking is so conservative, we only think of infiltration happening vertically down, but in these basins, it's happening on sideways as well. And there is a lot of infiltration going on. So EPA actually developed a specific curve just for these tighter soils, and show that you can get a lot of treatment, even still with the smaller systems, even with the tighter soil. And that's again because on this annual average basis, these smaller storms are getting captured and infiltrated, and that accumulates to a lot of water over an annual year. Again, we're not talking about, big storm events, but if we're thinking about that sort of cumulative effect, it can add up. So we're really promoting infiltration whenever you can, even when, again, the designer would say, oh, I can't, it's, everyone thinks it's just like impossible because all the rules have always said not to do it. And so having this data behind it, it can help show that this actually can make an impact and can be used and should be. So I just want to allude to other stuff that's in the manual, just because I couldn't cover everything today. We talk a little bit, and I don't know what the order of these slides are, because I think I also have an example, a mini case study, but we also talk about, we have these two checklists that are just help people think about retrofits. So is it, one's called like, is it the right site, and is it the right situation for a retrofit? So this is maybe more from like a planning approach concept where you're trying to find, you have X amount of dollars to do some stormwater improvements in this whole watershed. What should I do, as a retrofit? And so these checklists help kind of make you think of all the right things. Like, is this the right site? What are the issues on the site? What are the constraints? And is this the right situation? Who's the owner? What's, who's going to maintain it? All those types of things. So we have those checklists in there. We have a bunch of tools, or really references to these existing tools, that help you use the curves. We also have all the curves as appendices visually and as numbers. But we also, there's a bunch of people have developed curves. UNH Stormwater Center has developed a curve set, like an interactive, like, Excel kind of thing where you can type in like, I have this BMP, this size, like what's the performance? It's basically just doing all the lookups for you. So there's a handful of tools out there that do that, and it's all referencing the same data. So that's good. We talk about some thoughts about if you are truly retrofitting an existing traditional approach, you have a detention basin that's not that helpful. How can I get it to have more water quality improvement? So we give some ideas for that. We talk about I&M planning considerations. And so I&M is inspection and maintenance, because that's honestly what we're talking about here. We always use O&M like operation and maintenance, but inspection is a big part of it. How do I get to the site? What do I need to look for? How do I plan my BMP so that it supports sort of the longevity of it? And then we actually do go through each of the different categories of SCMs, BMPs, and each of them individually. And we don't necessarily give all the design guidance for each one. We don't give specs or details. What we do instead is we have these pretty annotated images, like the one you're seeing on the right. This is an example of one of our cut sheets. We talk a little bit about what are the specific concerns for that particular BMP. Not every little design criteria you might need to think about, but like I always say, like if I was talking to like a coworker and they're like, I'm going to be designing an infiltration system, like what do I need to know? I'd be like, oh, well, you need to think about your outlet control. You got to think about velocities if it's a swale. And, you have these check dams, blah, blah, blah. These are like the top like things that I would say are really important that you need to think about to make sure it functions right. So again, this isn't meant to like serve as a standalone design thing. This is kind of supplemental to someone who's been doing this already, but maybe not used to thinking creatively in the retrofit scenario, or maybe this BMP is a little different than one that they've done before. So we give kind of, hopefully it's like unique guidance that's not stuff you just see somewhere else regurgitated. That was our goal, is not to just kind of repeat the same stuff that's out there everywhere else. So I wanted to just step through one example, I think, is what I have. I'm sorry, I have like 6 different slideshows. So I'm like, which one's in here? But, this is an example. Oh, this is something we talk about of just how to approach retrofits. And so I was kind of alluding to this, is there's kind of 2 different ways that these retrofits happen. One is this planning approach on the left, and that's where you, like I said, maybe you have this watershed goal, maybe your municipality or a whole, watershed organization or whatever it is, and you got grant money or you have this opportunity to plan out a project, but you don't know where to begin or what to prioritize or how to think about it. And so that we step through that approach to retrofits, that sort of more methodical, big picture planning approach. And we step through these different steps and talk about, how to do them and what to think about, and talk about some of these tools and how to use the manual to support that as well. This other approach we're calling the opportunistic approach. And this is where you are doing something, some work is being already planned for whatever reason, like we're redoing the parking lot. How do you get a retrofit incorporated into those opportunities? Because those are really the cost-effective ways of doing retrofits, because you're already have people on site, you're already paying for construction, blah, blah, blah. So, we can add 5%, 10% to the project cost and get stormwater treatment. And so being, some considerations of how to be ready for those and how to kind of have a system for that. One example we love to use is the city of Arlington, Mass. has done this greatly. Like they've basically created their own standard detail of how to take a normal catch basin drainage system and do a little outlet to an underground infiltration trench, just like basically it's like a gravel pit. And these catch basins send a certain prescribed amount of water to that little gravel pit. And once the catch basin fills up enough, it keeps going down to its normal drainage system downstream. And so they, pretty simple concept, pretty simple design. They standardized the detail for it. They know the materials now whenever they do a roadway project, they just put these in. And so that's like the idealistic version of the opportunistic approach, right? But it's like thinking about what type of things you can do when you're doing work anyways, because that's the cost-effective time to deal with these existing developed sites. So yeah, we kind of talk about some considerations for that. So one example I wanted to give was the RIDOT work we're doing. So we're working with Rhode Island Department of Transportation. They are in a situation with their agency-wide stormwater permit where they need to go back and do these watershed assessments for each of the watersheds where they discharge to impaired waters. So it's kind of like the whole state, not really. But if you look at this map of Rhode Island, you can see they've been doing chipping away at these watershed assessments. They have some that are already completed, others that are in progress, some submitted to EPA and DEM is the state agency there. And anyways, we've been supporting them for years on doing these watershed assessments, which is why we've gotten so into retrofits and why, VHB helped write this manual, is because we've been doing this for years. But I wanted to give an example. This is an example of the planning approach where they're going back into a watershed and looking at their property, in which case they have very linear property boundaries, tight corridors. They don't own everything in the area. Drainage doesn't follow necessarily their property boundaries. So this is, the classic retrofit where you're constrained and just trying to do the best you can sort of after the fact, and understanding that your site has a primary purpose, which is not stormwater. It's, safe roadway, transportation and safety. So we have gotten, really used to going back and saying, okay, let's look at each of the little pieces of the area and talk about, is this area even feasible for doing stormwater control? Some areas, the slope is just way too steep. It's an embankment. It's a bridge over something. You can't do anything down there. Other areas, they already have in design for retrofits. Other areas are just considered potential. And so you can kind of characterize these areas as, does this have opportunity for a retrofit? Is it something simple? Like sometimes they'll have a swale going down the median, and all they need to do is add a little bit of outlet control through check dams or just raise the outlet structure. And now that swale provides some retention, infiltration, and has become like a water quality feature. So some stuff is low-hanging fruit like that. Other stuff, it's like, well, we could do something, but it's so complicated that it's probably not worth it as a retrofit, but it's something that you could do in that opportunistic approach. Like when you're, repaving the road or redoing, an overpass or something, that's when you would do that measure. So sort of this planning approach of assessing also a site and say, what can I do here? I have this type of soils, I have this type of drainage, I have this type of, discharge downstream, and trying to evaluate that. So,
sorry, quick question on the Rhode Island example. Are you aware if New Hampshire has anything that's similar? I know that I'm not aware of anything, but I'm not totally in your world.
Yeah, New Hampshire. So Rhode Island is and Massachusetts honestly are both ahead of the game in this situation, in this arena, because both not by choice, but because of legal issues. So they, for different reasons, got in trouble for their stormwater discharges and were forced to do these retrofit programs, starting years ago. And now what you're seeing is this type of requirement to do retrofits and do this type of stormwater improvement in the MS4 permits. So if you know what I'm talking about, like the municipal separate storm sewer permits, but the DOTs have those permits too, even though they're not a municipality. So they're it's getting written into just the regular permits. So the municipalities and the DOTs have to do this. New Hampshire being one of them. So the New Hampshire MS4 permit requires, at least the planning and review for retrofits, and, the installation of them at wide scale is still not fully required, but they are, it's coming around, and like I said, some of the two agencies that we've been working for that are doing this already are doing it not because they were in these unique situations, but that's this approach is kind of becoming the adopted approach. And like Vermont has that residual designation authority permit too for those large scale impervious areas. So like that's like this too. It's like you have to go back and retrofit. So how do I figure that out? That's that planning approach kind of concept.
Are the new
Where-
are the Vermont stormwater management plans, are those part of that permitting process in Vermont? I mean, that they just started that the last couple of years.
Yeah, so the Vermont MS4 and all the Lake Champlain stuff, they also have those like phosphorus control plans. And if that's what you're talking about, that is very much this planning approach concept where and then like for New Hampshire, it's like Great Bay. I know you guys are a different watershed, but it's like it's that sort of go back. I need to come up with a plan. I need to prioritize. I need to have these projects sort of ready to go when I have my funding. It's popping up in a lot of the different regulatory programs that way. And so that's what I was saying. It's like the people working on those types of plans and trying to come up with these ideas are the ones that are the same designers that are just have been working on the site design types of projects, like the new and redevelopment projects, and they're the ones ingrained in the state manuals, and I have to follow 1 inch, I have to do it this way. So they're going back and trying to be planning these things, but they're just so rigid in their approach to that they're saying, well, that's not enough space, or I can't fit that. And like I said, we're showing it can be smaller, it can be this, you can do it flexible, So that's where this manual is trying to kind of like bridge the two worlds. And also, even when you are on a redevelopment site, some states allow this like maximum extent practicable kind of concept. And, these measures are great to say, I did the best I could, yeah, I didn't follow your whole prescribed guidance, but I still did all the stuff. And here's, I can even credit it for you and show you how beneficial it is. So yeah, I might not be talking the same words about which permits are what, but it's like it's out there and being required more and more. And like I said, working with some of these agencies who have been doing it for years, put us in a spot where like, EPA and UNH was like, hey, we want you guys to help us write this because you've been helping these agencies do these programs for years. And then it was great because we could be like, okay, here's all the things that matter and here's all the things that don't matter. And that's kind of what this slide is. It's like, RIDOT has, we've learned through these, like, what are the challenges and lessons learned? First of all, working with designers who are kind of just, this is the way you do it, and not kind of breaking out that creativity or sort of different way of thinking because they're just used to saying, oh, I have to check all these boxes. Oops, I didn't mean to click. Just providing enough treatment to meet the goals, sizing it to what you need, not just sizing it to a set number. Through this Rhode Island program, we were able to actually develop some new credits for some new measures and help EPA. And that's some of the stuff in the manual we actually developed or through the RIDOT program because it was so important for them to have even more choices and more flexibility. And then just, really some ideas about how to prioritize, after you look at these sites enough, you're like, oh, that would be great for it. That wouldn't. And, you can kind of get those rules of thumb, and we try to incorporate those concepts as much as possible in the manual. All right, so I think I said all this stuff already. I probably don't need to go through all these conclusions all over again, but here's the link to the manual. And like I said, there is a 2-page sheet that is probably nice to skim and pass on to someone if you think, oh, you might be interested in this. We tried to make that short and sweet and, easy to share. Just wanted to mention that again, we worked with EPA and the SNAP network on this. Elizabeth and Kim were the two representatives from SNAP, and then the technical advisory committee. We tried to get all the states represented, and UNH Stormwater Center was essentially representing New Hampshire DES. They're actually getting the Stormwater Center is actually working with DES to update their state manual. So a lot of this will be incorporated into the New Hampshire manual. I'm guessing, I'm hoping, since they worked on this, and this is kind of a stepping stone. But you can see we worked with a lot of the different states and EPA, and our goal is to get the different state agencies, environmental agencies, to adopt this in some form or fashion. We know it's not going to replace their regulations, but how can they see how this tool fits in with their approach? So there's my contact info, and if there's any other questions, I can stay on. I'm going to stop sharing just for a second so I can see. So feel free to ask any questions, or if everyone wants to go eat dinner, that's fine.
We do have another question in the chat. If you're familiar with the New Hampshire Soak Up the Rain program, that's really focused on residential modifications to manage stormwater, and whether or not, what do you think of that program and those types of retrofits, and whether or not they're effective, if they're beneficial to the watershed?
Yeah, I'm loosely familiar. I mean, I've definitely heard of the organization and kind of know what they're doing. I don't know the specific things they're promoting. And I know when you get into the residential level, what can I do at my house? It's a similar concept to what we're talking about when you talk about those unit operations and processes. We're talking about how to infiltrate it, how to get your driveway to go into your lawn disconnected instead of the road where it's just going to go in the catch basin and down to the ocean or the river, So it's the same concepts, but you're probably getting on a different scale. So when you're talking about a residential thing, you're talking about a rain barrel, or you're talking about a rain garden. It's the same things, but again, these different names. And so I'm guessing they're all really great, and each little piece can incrementally help. I know when I redid my driveway, it's going to drain into my lawn, and we had the roof drain go into this gravel pit underground. We made our own leaching basin just from gravel, and and just stuff like that. It's all the same concept. So I think it's great. Unfortunately, or sometimes those things, they don't add up as fast as you want them to. I mean, when you really look at a community, and you look at the impervious cover, because that's the biggest stormwater impact, is the impervious areas. It's usually the roadways and the highways and the big industrial parks and the big buildings, the big box buildings. And that's why these new permits are coming out to tackle those large impervious areas. So, we've done some work for municipalities, and, yes, those programs are great. It makes people aware, and it can incrementally help, but, they have to start figuring out what they're doing with their roadway, the stuff that adds up. It's kind of I always think of it when you have water issues and you have a leaky pipe, and you're telling everyone to turn the water off when you brush your teeth. It's well, yeah, that's great, but you got a leaky pipe over here, you got to fix that, because that's, in terms of how much you can move the needle. So I don't want to discourage it, and I think it's awesome. And like I said, I do it myself, but in terms of a bigger impact, you need to tackle the big stuff. So.
Great.
Any other questions?
I had one question about the kind of the economic argument for this, especially you're talking about, things that aren't required necessarily by a permit. These might be more optional techniques. Also, maybe how do you convince a municipality to do retrofits along their roads to improve the water quality? What are the economic arguments? And I guess one specific question I have is, a lot of communities are really concerned about culverts. Is there any not water quality related, but maybe if it reduces the sediment going into culverts and the ability, not having to clean out those culverts as much, but also the flow of water
Yep.
into those pipes, and whether or not, can that keep smaller pipes running longer rather than having to replace them again? That's kind of
Right.
two questions there, more general and specific one, but how far do these go, and what's the return?
Yeah. I mean, this is mostly, is focused on water quality, but I think, it all is connected. It's the same water. And when you're talking about like culverts and infrastructure and all that, one interesting thing is that VTrans is working with UVM on a study to develop and quantify, again, the improvement of if you were to repair, these eroding banks, or, at an outfall where it just continually erodes and you see those like perched pipes, and you see those at culverts, you see them at outfalls from, bigger drainage systems. And if you prevent those and repair those, how much have you saved in terms of just sediment transport that's being deposited somewhere else? And, Vermont with the steeper slopes, the higher flows have, they even have those like the flow-based TMDLs. That that flow is does create the water quality issues. So in those more like flashier systems with steeper areas, so it is related, and it is hard to get attention on it because it's not a flood. It's not, my backyard's full of water. It's like, well, you're not going to go build a tiny rain garden. You're going to, you need something bigger to like, control those flows, and you do the detention and get the timing right. So like these smaller measures, you shouldn't expect them to, fix the 100-year flood, and so that I just like to bring up that sometimes in terms of reality, because I think a lot of people, you hear it all the time. It's like, we did green infrastructure for resiliency. It's like, well, the little tree box filter in that urban area is not going to save you when it's like, like I said, a 100-year storm. And so we have to be realistic about like the sizing and what these things are. So, going back to like convincing people it's important, it's usually has to be some water quality issue, a regulatory issue, or, you're seeing algae blooms like in your prized water body, or there's some impact to something that, is driving people to do it. That's not, if it's not regulatorily forced, it has to be another driver right now, and that's kind of the way it is, so you get these, watershed groups, what you guys are doing are saying it is important, and it can be simple. And I think that's what we're trying to promote, is that it doesn't have to be really expensive, really annoying, really complicated. It can be simple. And so, showing a simple add-on to like a roadway project that only adds a couple percent in cost, like you have to get the right person at the municipality to kind of push that through, and you need this to make it cost effective and show that it's still useful, though, like cost effective. It's cheaper, but it's still doing something. So it's a little bit of an uphill battle when you don't have like the regulations breathing down your neck. So it is kind of what it is right now. And that's why we're seeing more regulatory action, because CLF, like Conservation Land Foundation, like groups like you guys, you're like, hey, we need to do this, the louder that is, the more, we will see it.
Thanks, Theresa. There's a question in the chat from Keith Alberson. Well, a comment, and just curious of your thoughts. He says, big storms, really big ones, can flood places with non-conventional pollutants, things like garbage dumps, chemical plants, hazardous waste sites. This is a comment, not question, but if you have any thoughts on the topic, he's curious.
Yeah. I mean, though, I feel like these are the next like set of challenges, like on a bigger picture, is the resiliency, like flood type stuff, and everyone is right now focused on the quantity issues with that, but they're not thinking about you know, what else it's doing. And I think I don't have any, you know, specific thoughts on that. I think we're trying to tackle the day-to-day and the annual average stuff so that these water bodies aren't accumulating, you know, pollutants and getting overloaded in the long haul. I think there's any sort of chance for like an extreme event that could send things out of whack. But, you know, on a different side of things, you know, we talk about climate change from the point of view of these bigger events, but climate change also means potentially more wet events in a row, or dry and then drier periods, and just sort of different hydrologic patterns. And I think that is what you'll see affect the water quality as the climate changes. And then, you know, these big events might create, you know, just issues, things getting washed out, you know, like you said, a spill or something like that, that has to be kind of dealt with as like a one-time major event. So yeah, I mean, things are changing, and this manual is kind of tackling the widespread sort of day-to-day common like pollution. So. All right, well, I encourage you to check it out, and if you have any questions, let me know. Feel free to share this like widely. I would love for this not to be a manual that sits on a shelf or in a virtual shelf and, you know, people forget about it, because I know there's lots of those. You know, I think it has a lot of good information in it, and what it does too is it ties together a lot of the guidance that's already out there in the different New England states and puts it in a guidance manual instead of buried in these various regulatory programs. So don't be afraid to like reference it and tell people about it, because it is the same information that, you know, these different states are using in different ways. So it's not like obscure new research. It's just really more compiled and presented so that people could start using it, and we could kind of break down really the excuses that are used to not do anything. So I hope you guys find it useful.
Thank you, Theresa. I know a couple people have already said thank you in the chat. And I thank you very much for the great presentation and for joining us tonight.